Okay, very good. Now. All right.
So what are we doing?
You made it?
No.
What?
Yeah.
Oh, you?
I know usually would help.
Yeah, I must have been upset. Get him
Yeah.
down.
Me. I don't say. I'm always the same.
He commented on the.
That's about it. It's something my chapter 4. Try again.
Oh, you did?
How's research going, Swamya?
It's good. I have have a lot more time to kind of look at my dissertation topic.
Oh, all right.
So slowly getting started on finalizing that and getting more work done on it. But otherwise, our testing that we were doing last semester could wrap up in this semester. I just don't know when.
Oh, okay. That happens.
Yeah,
Very nice.
we're probably gonna come back to test a couple more times in the TVAC upstairs. So once that's done, at least that's not gonna take any more of my time. So but it's been a really
I know you
fun,
want- I know you
fruitful
want to see it.
experience.
It's my first newborn kid. Is your car?
That should work. Where's it?
Yeah, you said it's just somewhere from us.
They see that. Speak on the floor. Cool. That's good. But everyone, yeah, it takes a second. Yes.
All right.
I thought done.
All right. Where is everybody turning in their homework, huh? I guess we're kind of early. What's up, man? How are you?
Yeah.
Is it good?
Projector.
You still working on your finite elements or what?
Yeah, I'm a full.
Oh, really?
Yeah.
Wait, qual exam. Okay. Already? So did what's the name schedule it for you already? Ahmed?
What?
So normally they have to be scheduled through the chair of the electromagnetics area.
I'm doing photonics.
Oh, really? Yeah, but I think it still falls under that. Or maybe not. Okay. I have a student also that's going to be taking it, but they didn't give him a schedule yet. So I'm surprised yours is already. That's why I asked. Great.
Ever since it's sort of hectic.
Yeah. Quals are important. You got to pass those. Make sure you.
I don't feel like I'm.
Think you'll be all right. Who's in your committee?
What?
Who's in the committee?
Um.
Look at that end.
Off the top of my head.
I'm serious, I don't.
Very good.
Can't accept this. I don't know. No, there's just one first aid. This one. So it's like.
All right. Thank you.
I emailed, Lauren to-
Yeah, I saw that. How was it?
Oh, I didn't put too much like, more.
Homework wasn't too bad though? Good. Very nice.
I found this book useful.
Which book?
These kind of waveguide.
Collins? Oh no, wait. Oh, Marcuzzi. How do you say his name again? Markowitz?
Recurrent.
Yeah. He did a lot of work in waveguides. Yeah, that's a good book.
Clarify the transfer, the resonance network. Oh, it's these graphs related by hand.
Oh yeah.
These take forever to make and they're done by hand.
Yeah.
So it's some grad student. The ruler. Then they photocopy it.
How's it going? Very nice.
I tried to understand why you chose cosine.
On we'll go over that today. When we did the derivation of the HEM modes. Yeah, we'll see why. We'll see the consequence of choosing cosine. It leads to exactly what I thought, right? You'll derive similar expressions for the sine if you choose sine instead, and then you'll just have modes that are rotated 90 degrees because of the circular symmetry. So when you calculate HEM mode dispersion, then you'll see there's a bunch of degeneracy in there. We'll talk about it today. Were you able to restart that simulation?
Yeah, I did, yeah.
Very good. The observation plane. I think that'll be nice to see the effects of not including that incident angle. I think I'm gonna order that box. I've been thinking about it. We'll probably need it. It's like a enclosed anechoic chamber.
dimensional circuits.
We were gonna
Closet or is it like a?
kind of. It's like a chamber. We were gonna build one ourselves, but I think and you could do that, but in the end, you might.
And they put our chambers.
Yes. So
Yeah, I think we'll probably buy it.
she said,
What?
did they send you?
Yeah, they did.
Is it just solid copper or is it aluminum?
That's a good question. I need to ask them if it has the shielding from the outside. If you use absorber, you kind of absorb everything radiating from inside, but you also want to use metal around the outside so that nothing gets in from outside.
But I don't think in that frequency noise gonna bother us. I mean, it's good to be shielded, but
Yeah, we'll have to.
Well, it's.
Okay.
Facing the feature. Somebody else is in a different frequency rather than us.
For sure.
So it's just total shield range. Rather than.
That's right.
Circumstantial.
Okay, so let's get started. It's 4:00. So by now you guys have all turned in your homework. You emailed me your gifts, and I'll go through them and I'll select the winner of which one is the most most elaborate and all of that. So that person will get 5 extra points on their homework, which is cool. So hopefully you guys have now gone through the experience of one of the homeworks in the class and you're all still here, which is good. So but these things are important, man. You don't, yeah, there's active and passive learning. You're watching the lectures, you're only gonna hear it, but you're not gonna think about it, right? So you want to work through the problems and convert it into knowledge that's birthed in your own mind, right? Instead of being told about a problem from somebody else's perspective. When you go to solve the problem or rederive it or try to, make sense of it in your own words, that's when it becomes your knowledge, right? So it's important to do that. All right. Okay, so let's review really quick what we're doing. We're solving the problem of circular dielectric waveguides. We have a dielectric rod, which is infinite in length, and it has permittivity epsilon d mu d, and it's suspended in free space, all right? And it has radius a. And what did we do last time? We derived the HEM modes by considering the fields inside of the dielectric first, and then we said that the HEM modes are a combination of the TE and TM modes, and the TE and TM modes that have cosine symmetry are going to be derived and considered as the HEM modes. We could have started off choosing sine of M phi symmetry, and we would have gotten a similar result, but in the end, it's just a 90-degree rotation of what you got. So here we chose cosine of M phi. We combine the TE and TM modes to get the hybrid EM modes, and we derived those for the dielectric region. Then we looked at evanescent decay using the Bessel functions of the second kind. And we wrote the fields outside of the dielectric rod. And then we used boundary conditions to construct this system of equations with 4 unknowns, 4 equations and 4 unknowns. These 4 equations here are arising from these 4 boundary conditions. The 4 unknowns are AM, BM, CM, and DM. Here's CM here and DM there. And we recast this system of 4 equations and 4 unknowns into a matrix equation in the following form. But before we did that, we redefined our wave numbers from beta rho, alpha rho, and beta z into chi, xi, and zeta. All right? Nothing but the wave numbers themselves, but scaled by the radius of the waveguide. And what that does is make this system unitless, right? These are unitless numbers, and they apply to various combinations of electrical sizes of rods or operating frequencies and different radii of the dielectric rod. All right? And then we solved this system of equations, this matrix equation, which is equal to 0. It's a homogeneous matrix equation. And to solve that, we said that the determinant of this the determinant of the F matrix or the coefficient matrix has to be equal to 0, right? To make this matrix singular, because you want it to be equal to 0 and therefore non-invertible or have linearly dependent rows or columns, and setting the determinant equal to 0 enforces that, right? So by doing that, we came up with this expression, and this expression we recast into this eigenvalue equation here, which is G1 times G2 minus G3 squared equal to 0. And it's a function of chi, right? So the entire expression, or this entire eigenvalue equation, is a function of chi. So solving this, finding the chi, which satisfy this equality, lead to what are called the eigenvalues, basically, right? All right, so G1, G2, and G3 here are shown as this expression here. G2 is like that, and G3 is like that. All right? Okay. All right. Then we proceeded to solve the eigenvalue equation. We took a limiting case for m equal to 0. We knew that m equal to 0 is the only way to lead to azimuthal invariant modes. And we said in the beginning of the lecture that modes that are azimuthally invariant can be classified as pure TE to Z or pure TM to Z. All right? If there's any azimuthal variations, then it becomes a hybrid electromagnetic mode or HEM mode, and that HEM mode necessarily cannot have an m equal to 0. So m equal to 0 immediately gives you the eigenvalue equations for the TM 0M modes and the TE 0N modes, where the first index, which is normally m, is now always equal to 0. All right? Good. And in this case, you get these two dispersion, or not dispersion, these are eigenvalue equations, all right? They probably could be seen as a dispersion equation, but all right. And I said you will write a program to solve these in your homework. So pay attention to today's lecture because this is going to be part of your homework coming up. All right. And then we showed some plots from your book. These are from Balanis's book for the solution to these eigenvalue equations. And they're plotting chi here as a function of beta naught A, right? They're plotting chi as a function of beta naught A for two different cases, epsilon r equal to 20 and epsilon r equal to 38. All right? And we're going to go through, okay, so then once you have chi, you can find zeta and xc, which means you can find beta z and alpha, right? And here's a plot of beta z divided by beta naught as a function of 2a over lambda taken from your book as well. That shows for a polystyrene rod of epsilon r equal to 2.56, which shows that beta z here, HE11 is the same as HEM11, and that mode starts out with a wave number that is approximately beta naught, right? Which means very weakly bound to the waveguide. As you increase the electrical radius of this thing, then you start to pick up, the wave number increases, right? Beta z becomes greater than beta naught by this factor on the y-axis, all right? And then this table here shows the order of these modes. So here we have HE11, which is also HEM11, right? In different notation, is the first mode that appears. It's a dominant mode, it always appears. It has a chi10 cutoff of 0, right? Which means it's always there. And this solution comes from, if you go back to the eigenvalue equation, you can set J1 of chi10 equal to 0, and that will satisfy the eigenvalue equation. And from this, you get two modes here. Why do you think there are two modes?
Hybrids.
So the hybrid mode is a combination of TE and TM modes, but it's its own mode, right? So there are, whenever you see two modes for the same, with the same cutoff frequency. Yes?
Degenerate modes with the symmetry with respect to phi.
Very good. They are degenerate modes. There are two of them. Why? Because one of them is the cosine m phi that we started with, but you can do the whole entire analysis starting with the sine of m phi symmetry. And if you do that, you'll get the same mode, but it'll be rotated by 90 degrees, right? The same cutoff frequency. All right. And then the next modes that appear are TE01, TM01, and HEM21. All right. And those come from setting J0 equal to 0. They have this chi at the cutoff, and there are 6 of those modes. Yes.
Are there any like particular consequences of degenerate modes other than that you like when you reach that cutoff frequency, you will always excite both modes at the same time, right?
Not necessarily, it depends. So these are all supported eigenmodes, right? That the waveguide supports. But you still have to excite them, you have to couple to them. So if they're orthogonal and you put a probe vertical, then you might only couple to one of them, right? So they both exist in the waveguide. If you excite it at a 45-degree angle, which is hard to define in cylindrical symmetry, but maybe you can excite them both, right?
And what is like, why are they called degenerate? What is that implying?
Degenerate, that's a good question. I think it implies like what I interpreted it as is two modes that have the same eigenvalue and the same eigenvector, right? Okay, good. So you can't tell them apart, right? All right, and then we have HE12. So where do all these come from? Let's go here. Let's say we start here at 1.5, and this is at 1.5, if you define the x-axis value, you've defined the permittivity and the operating frequency, or one or the other, right? You need to at least fix one of these. So what do we pick up in order here? The HEM mode 1.1 is first, then TE01, then HEM21, then TM01, then HEM12. There are all these modes, right? They're all in this table here, in this order, right? Okay, good. This is the order of the modes. All right, so I spent most of the weekend going to create this example for you. And so this is the example. So consider the non-magnetic dielectric waveguide of radius A is 1.5 divided by beta naught at f equals to 10 gigahertz and a permittivity epsilon r equal to 38. So here's the problem. It's an infinite dielectric rod. Radius A, which is equal to 1.5 divided by beta naught. If you know the frequency f equal to 10 gigahertz, then you know beta naught. So the radius is fixed and the permittivity is fixed, right? The eigenvalue equation, I solved the eigenvalue equation by writing some code, which you're going to do as well. Writing a program to solve the TE01, TM01, and the HEM11 mode eigenvalue equation using a root finding algorithm that was built into MATLAB. So I didn't have to do anything for that, right? There's a bunch of solvers for finding roots or solving systems of transcendental equations or nonlinear equations in MATLAB, all right? The results are displayed on the figures to the right. So I obtained this figure first. This figure is analogous to this one, all right? This figure shows chi as a function of beta naught A, all right? So first thing I did was I recreated this one because our permittivity is 38, right? So here is a part of that graph. So for values between 0.5 or 0 and 0.8, I was getting some kind of funny results, but I didn't need those. So I started here at 0.8 and went to 2.5. And these are the curves here, right? So at beta naught A equal to 1.5 for the radius for the problem, we have this dashed line that's shown vertical. And I get this curve for the HEM11, then the TE01, then the TM01. Those three dispersion relations give me this plot. And this plot is exactly the same as this one. So here's my HEM11, the TE01, and the TM01. I did not plot the HEM21. Although in principle, it's easy to get that one, right? Probably should have, but okay. Then this plot shows beta z over beta naught divided by, or as a function of 2a over lambda naught. So I recreated that one as well. All right? Well, I didn't recreate that one because this one is for 2.56 and we're using 38. But I made a very similar plot, all right? Okay, so that is all of these plots here, this data here. So I have it for, sorry, hold on one second. Okay, I have it for the HEM11, the TE01, and the TM01 mode. Okay, so we solved those eigenvalue equations and plotted the results of the root finding algorithm here. Once you have chi, you can find beta z easily, divided by beta naught, and make this plot, all right? Okay, so the eigenvalue equation is solved, and the results are displayed in these figures. A is equal to 1.5 over beta naught, but beta naught is 2 pi over lambda naught. So A is equal to 0.0072 meters, right? And 2A over lambda naught, which you need for this x-axis on the figure on the right, the lower figure, is equal to 1.5 divided by pi, because here's A, right? If I multiply A by 2, so here's A. If I multiply A by 2, then these two cancel. I get 1.5 lambda naught divided by pi, which is here, but I divide it by lambda naught. So it all agrees. That's 0.4775. All right. So from the upper figure, at beta naught A equal to 1.5, which is this dashed line here, we can read off the values of chi for the TE01 mode, the TM01 mode, and the HEM11 mode. All right. Those are these values here, here, and here. All right. Good. We get 3.4365, 3.82, and 2.3. All right. Now, from there, we can calculate zeta and xc and get beta z and alpha naught. And then we can plot beta z as a function of 2a over lambda naught to get this figure on the lower right. All right? From the lower figure, okay, so there should be a divide here in a lambda naught. All right? From the lower figure, at 2a over lambda naught equal to 0.4775, we have the following values of the longitudinal wave number for these three modes, okay? So these are calculated values by solving the analytic problem of that crazy matrix we had, the eigenvalue equation, and solving it numerically to find these beta z's, right? That's what the whole point of these problems are when you're solving waveguiding and transmission line problems, is you need to find the wave numbers, right? Wave numbers and field profiles and impedances. But here we find beta z from the chi's, right? So that's an analytic solution. Now, I also went to CST Microwave Studio and I ran a simulation there. So the simulation that I ran there was of a dielectric waveguide, the same problem. Dielectric waveguide, I put a port on the front and back and calculated the modes. So I think there's a cylinder here, like that. I put a port here and a port there. This thing had epsilon r equal to 38. I think I used about 1 wavelength here, and this radius was A, right? And I did the simulation in CST Microwave Studio. And I exported the results. So here, beta naught A is 1.5. So there's this red dashed line here. We really have a bunch of modes here, right? There are 19 of them in this plot. All of them exist at this radius and frequency. But I only calculated the first 7 because when you define a port in CST, you can select how many modes you want to consider. I only considered the first 7. But I probably could have considered more. So the first 7 are obviously going to be the first 7 intersections in the vertical direction, right? Okay, so how do we read this plot that I exported from? I exported the data and post-processed it in MATLAB. Exported from CST, post-processed in MATLAB. So I'm plotting beta z over beta naught. And this is the mode number that you get from CST, because CST gives you beta z, right? So CST results are these dots. This one, this one, this one, that one, this one, that one, and that one. The beta z's I got for each of the 7 modes. And then I plotted as a vertical line what the analytic solution was for these 3 different modes that we got from solving the eigenvalue equation through the root finding procedure. All right, so what do we notice? The first mode that CST finds, it calls mode 1 and mode 2, are degenerate modes, right? We expect that. They're hybrid electromagnetic modes. The dominant mode is HEM11. So we should have 2 modes. They're degenerate because of the sine and cosine symmetry, and they're both approximately what we calculated analytically for the HEM11 mode, right? Okay. The next mode is mode number 3, and mode number 3 has 1 dot, right? And it is a TE01 mode. All right, very good. And we're somewhat close to the analytic calculation there too, right? Mode number 4 and number 5, so we expect these to be this order, right? So look here. Mode number 1 is here. That is HEM11. Those are these 2 ones, right? Mode number 2 should be TE01. Mode number 3 okay, so this should be 1 and 2 because they're degenerate. This should be 3. This one should be 4 and 5, which is HEM21 because they're degenerate. It's a hybrid mode. Then we have TM01, which should be mode 6. And mode 7 is going to be one of the HEM12 modes, right?
What does EH mean?
That's the other notation for the modes. They're EH or HE, depending on whether TE mode part of the hybrid mode dominates or the TM part of the hybrid mode dominates. But HEM is the mode nomenclature that we're going to use, all right? It's just a different way to describe the same mode. So here's the hybrid electromagnetic mode HEM21. We get these two wave numbers from CST. The TM01 mode, okay, so this should be, so I haven't gotten a chance to understand why this is slightly off, these two values, right? This black line here, which is supposed to be the TM01 mode, intersects the hybrid electromagnetic mode, but it's really not for that mode, it's for TM, right? So these two happen to be around that same wave number.
So these three should be degenerate.
The hybrid, all the hybrid modes are degenerate, right? But it looks like this black curve here, the analytic solution for TM01, corresponds with the hybrid electromagnetic modes in CST, the HEM21, right? But I don't think that's the case. It's just a coincidence of how close we were with the numerical solution. So this black curve is supposed to go with the TM01 mode, and I haven't dug into why it's slightly off, right? Okay. Nonetheless, and then the hybrid.
See, that HEM21 is between TE and TM. So when you go back to the dispersion plot, you can actually see that would mean that HEM would go in between those curves.
Yeah, so here's TE, right? Here's TE. And then here's TM, but this HEM mode is in between right here, right?
Yeah, and
So
then
these two are in between, that's
on
true.
that Previous plot, a slide back. Or back more, yeah, here. See, it would be in between those two curves, and those two curves are very close to each other. So it would be easy to confuse. Well, the numbers would be very close.
Yeah, I mean, I think it's a numerical thing. I could probably improve it, right, if I spent more time on it. That's my conclusion. But okay, shows the general trend, right? All right. So then I exported the eigenmodes from CST and I started to match them up. We know what they should be, right, based on the wave number and solving the dispersion or solving the eigenvalue equation. Here is the HEM11 mode plot from your book, which is taken from sort of an analytic solution. And what do we see here? The electric field is the solid lines, and they are going, the solid lines are going horizontal, right? So it's a constant, almost a constant, right? They're weaker and then stronger and then weaker in the horizontal direction, but there's no variation, right? Or I guess there is variation from like this, right? And then the magnetic field goes down, right? But there's no nulls or lobes, right? It's just kind of a Gaussian looking thing. What do we have here in CST? The electric field goes like that, weak to strong to weak, and then the magnetic field goes down, right? Weak to strong to weak. Now, so that means that but the electric field loops like this, right? It loops in the horizontal plane, and the magnetic field loops in the vertical plane because it's a hybrid mode, and there is EZ and HZ, right? So you can see it here. The electric field loops in the vertical plane like this, and the horizontal plane. The magnetic field loops in the vertical plane. And the same thing, you can imagine if you extend this, it would go like this, right? Kind of a poor picture, but it's orthogonal, right? Hybrid mode. All right. The next mode is TE01, which is mode 3, because mode 1 and 2 in CST were degenerate. They were just the same picture, but rotated by 90 degrees. TE01, we have the electric field completely transverse to Z because it's TE mode, and it has no variation because the first index is 0 in azimuth. So they're rings, right? Here's the electric field from CST, it's rings, yeah? The magnetic field magnetic field makes loops along the, it makes loops in the Z direction and comes back down radial. So it has Z and rho components, right? but no phi. So, if you do a cross section, it looks like it's converging to the center, but really it's coming out in this plane, going across and then looping back down along the axis, right? The z-axis. You probably can't see it very well from where you're sitting, but take a look at these when you get your notes, when you're after class, right? Oh, you have all the notes. Okay, then the next mode was TM01. That's a magnetic mode, transverse magnetic. So here it's the dual kind of thing. The magnetic field starts to make loops. So here's the magnetic field looping, and the electric field now converges to the center, but really it's coming and doing a turnaround at this cross section, right? And it goes down the axis of the waveguide and comes back, right?
So in the hybrid mode, how do you know which one is the dominant?
Which mode is the dominant one?
I mean, when we have a hybrid mode, which one is the dominant, the magnetic mode or the electric? Because both are together.
No, okay, so all these modes exist independently, right? They will exist at different frequencies. Or if you're operating at a certain frequency, some of them will be above cutoff and some will be below, right? So the ones that are, if you're operating a frequency higher than the cutoff frequencies of these modes, then they will be excited or supported by the waveguide, all right? So this is the dominant mode, the HEM11 mode. It happens at any frequency, it's always there, right? And then the next mode is the, I don't know if it's the TE01. I don't know if I put these plots in the same order. Let me check. The next mode is HEM11, then TE01, then HEM21, then TM01, then HEM12, and so forth. All right. Now, each of these modes have an associated electric and a magnetic field, right? So if you go back to here, each of those modes have an electric and a magnetic field, right? Here's the equations for the hybrid electromagnetic modes, the electric and magnetic fields, as a function of the mode order, the index M. Yes?
How do you tell if it's like an HE or EH mode?
An HE or an EH mode.
Right, that was my
Like since HEM11 is a HE, like because the magnetic dominates, right? But how can we tell that?
That's a good point. You'd probably have to look at the coefficients that we're going to solve for that describe, there's a TM coefficient and TE coefficient, right? When the hybrid modes, the coefficient on the TE part and the TM part, and you combine them together. So you could probably look at the ratio of those coefficients. Okay, so yeah, so here's the TM01 mode and the electric field. This is mode 6 in CST. The electric field kind of converges just like it does in this plot, which is drawn from the analytic solutions, and the magnetic field rotates in the plane or in the cross section, right? Okay, and then here's two more modes. The first mode in your book, okay, so in your book it's HEN21, that's the next mode. HEN21 has this modal field pattern from the analytic solution in your book, and there's the E and H from CST. This was mode 4 in CST, and we can see that the electric field is doing, oh my goodness. I don't know what button I pressed. I just put my palm on it and it closes the thing. Okay, here's the electric field going this way, right? And like this. And we can see the same thing here in the electric field. It goes like this. I'll draw contours because it's kind of hard to see from where you're sitting where the arrows are going that way, that way, that way, and that way. All right? So that's that mode, yeah? And the magnetic field does similar, right? The magnetic field here, so that was the electric field. The magnetic field, the dashed lines, and they go this way and this way. And here's the magnetic field, it's doing this, and it's doing this, that, and that, right? So it looks like it's maybe 180 degrees out of phase, but this is the right plot. Okay, good. And finally, mode 7 is this mode, which is the HEM12 mode, right? Hybrid EM mode 1-2. And what do we see here? The electric field is making sort of this quadrupole looking pattern like this, right? And here's the electric field. And the electric field is doing this kind of thing. All right. And that's exactly what it's doing here. So it's a dipole actually, not a quadrupole, right? This one's also a dipole. It goes like that, and then it goes like that. All right, and then the magnetic field is doing the same thing, but it's rotated by 90 degrees. The magnetic field, yeah, the magnetic field is looping like this, right? So it's kind of doing the same thing here. All right, good. So those are the mode plots that you get from CST, right? So you can do numerical simulation of something simple like a dielectric rod waveguide, but you won't understand how it carries energy or how to excite or how to use it efficiently or how to design with it until you're able to break down the fields that would be transmitted by it or carried by it in terms of the modes that are supported by the dielectric rod waveguide. Then you can understand everything, right? You won't understand the dispersion and how you send something from one end to the other. It gets spread out in time due to the differing phase velocities of the modes, right? So this kind of, when you do a CST simulation, it gives you all these modes, but it's good to understand where they come from. All right? Any questions on that?
CST, how do you select the mode? By the excitation pole? Or?
No, so yeah, so in CST, you sort of draw like that. And here you define, this is a waveguide port, you define the number of modes that you want to consider at that port, and I considered 7, right? And what it will do in that waveguide port, the cross-section of the geometry, it's going to solve Maxwell's equations there, and it's going to apply the boundary conditions to the cross-section of the port, which is essentially what we've done to derive these modes, right? Okay, very good. So now that we have the eigenvalues that we used to solve the eigenvalue equation, we solved the eigenvalue equation, we got the eigenvalues. Those eigenvalues were derived such that at that value of chi, the determinant of f goes to 0, right? That's how we obtain the equation that we solved, the eigenvalue equation, setting the determinant of f equal to 0. So that means we can take those chi's, plug them back into the matrix, take the determinant of it, and we'll get 0, right? Okay, so that was the idea. So now we can solve for the unknown coefficients. Now that we've solved the eigenvalue equation and obtained the mode fields. To do this, we'll do this for the HEM11 dominant mode. For the dominant mode, we found chi to be 2.3. We can find C to be 15.032 and zeta to be 15.238. M is equal to 1 for this HEM11 mode. A was 0.0072 and omega is 10 gigahertz, yeah? 2 pi times 10 gigahertz, or yeah. Okay, so that means that our matrix equation now is like this, except all these numbers now we could substitute in zeta, chi, and we know omega here, we know m, we know zeta, and c, right? We know all these numbers now. We can construct an actual numerical matrix, right? If we know all of the variables and constants of this matrix, we can make an actual f with numerical values inside of it. If we took the determinant of that matrix, we expect to get 0, right? Okay. All right, so I'll come back to saying something about that. But now we need to solve for the coefficients, AM, BM, CM, and DM. But in linear algebra, if we're solving an equation of AX equals to 0, then really what we're looking for is the vectors X, the eigenvectors, which form a basis for the null space, right? So that means to do that in MATLAB, we can use this command null of A. It should be null, oh no, null of A because AX equal to 0. But actually we use null of F in actual, because if we call this F, right? All right, so this will give the basis of the null space, our eigenvectors, or these coefficients, of coefficients. So I did that in MATLAB, G equal to null of F. And okay, so for a long time, for like the whole day yesterday, I couldn't figure it out. First off, I solved the eigenvalue equation using root finding, got a chi. Then I plugged that chi into this matrix F, and I took the determinant and I was getting like 1 e to the minus 12. So not exactly 0, right? And I kept trying to debug my code and figure out why. I expected the determinant of this matrix to go to 0 because that was the whole premise of solving the eigenvalue equation. And it was close to 0. It was like 10 to the minus 12 or something, but not exactly 0. If it's not exactly 0, then this matrix will not be singular. If the determinant of f is not 0, then this matrix is not singular. Therefore, the null command will find, if it's not a singular matrix, it'll return empty all the time for the eigenvectors. And I kept getting empty, and I didn't know what the problem was. But the thing is, we're numerically solving this matrix equation, to find this chi that gives us numerically approximately 0 for the eigenvalue equation, right? But it can still be very close to determinant equal to 0, but not exactly. So this thing will have full rank and it won't have a null space, right? So what you have to do is use this second parameter I figured out. This second parameter says it's a tolerance that to set the singular values of f that are below this tolerance to 0. So if you have some lingering singular values of like 0.000000000, like 1, 2, 3, then that will give this thing full rank and this command null won't work. So what you do is you include the second parameter to the function null, and any of the singular values which are less than 1 e to the minus 8, it's going to set them equal to 0. Therefore making this rank not full rank and making it singular. And then you can, it'll find the eigenvectors. You'll find the null space, the eigenvectors that span the null space. All right, so that's a trick for your homework that you're gonna need to do. Anyway, if you do that and you include this singular value threshold, then what you get is these eigenvectors G, right? The G matrix or the G vector are these 4 values. So now we have A1, B1, C1, D1, right? And what you can do is you can go to your field expressions now. Now we have these coefficients, right? So we can go to the field expressions here, which are here, yeah? Yeah. So here, now we know AM, BM, we know all of these, right? BM, we know AM, BM. So these are all AMs and BMs, right, for inside the dielectric. If we go back to the solution here, what do we find? Here. It seems like those are kind of weak, right? A and B. So I just got these results, man. I haven't checked into them. So, but I believe that the solution's correct, but I need to go back and analyze, these coefficients. Do they make sense? But that would imply that the evanescent fields, which we get, which are the CMs and DMs, are stronger, yeah? Okay. Anyhow, that's the results, yeah? So this is the results. Good. So now you can go back to the field expressions and you can get the mode fields from these coefficients, right? All right, very good.
So we say that A is close to 0, so it really is from the second part that is.
I feel like these are backwards for some reason. So wait 1 second for your question. I don't know if this vector, I mean, I assumed that this vector was listed in the order A, B, C, D, because that's how we constructed this matrix. But I feel like this might be backwards. I don't know the ordering here. Maybe it has something to do with the ordering of the eigenvalues or something. I'll have to look into it. So it might be that this is the AM, which would make more sense to me. But I have to sit and think about it. All right, what was your question again?
Could we say that it is close to 0, so it really is just C? Because we're solving for coefficients, so how much effect is felt by A is really not that substantial compared to its pair.
So, okay, one other thing, we're kind of jumping the gun, right? Because we're assuming that this is like the strength of the field inside the dielectric and this is outside, but that might not be true. There's a bunch of other coefficients, beta z's and alphas and all these other m's, zetas, and then you have to unfold those or include those in the expressions. So with these coefficients, we have to really go back to the field expressions and plug these coefficients in to see really what the effect is. So I don't want to draw conclusions just from here yet, which is probably smart, right? Let's not do that yet. All right? Okay, yeah, so you could think of, since it's zero, it's, you know, but I don't want to think that way yet. Well, first, we should plug those into the field expressions and see what the actual coefficients of these terms, the different terms in the field expressions are. All right, good. So that's the end of the circular dielectric waveguide, yeah? All right, good. So you guys will have to do all that same stuff in your homework, all right? All right, so next we're going to study the circular dielectric resonator. It's the last thing we're going to study in this chapter. So these are very popular. That's why I want to make sure we include these into the lecture notes. These are used in a lot in resonators or sources or oscillators called dielectric resonator oscillators. They're used, I actually used them in my research at one point for infrared photodetectors that were coupled to these dielectric resonator antennas. But yeah, we're going to study these as the last topic in this lecture. So a dielectric resonator can be made from a high permittivity material cut into various shapes which mold the resonant frequency, right? Before, we did the same thing. We had a circular waveguide, and then we put PEC caps on the top and bottom of it, and that made a cavity resonator, right? We're going to do the same thing here. We had a dielectric waveguide. Now we're going to truncate it, so it's finite length in all dimensions, all right? We will study the circular dielectric resonator. In order to function as a resonant cavity, the dielectric constant of the materials must be large, usually 30 or greater, epsilon r, all right? Under those conditions, the dielectric air interface acts almost as an open circuit, which causes internal reflections and results in the confinement of energy in the dielectric material. The plane wave reflection coefficient at the air dielectric interface then is gamma, which is eta naught outside and eta inside. The plane wave reflection coefficient at the air dielectric interface is eta naught minus eta over eta naught plus eta, right? They're non-magnetic, so it's the square root of epsilon r minus 1 over the square root of epsilon r plus 1. As epsilon r approaches to infinity, this approaches to a reflection coefficient of plus 1, right?
So what does the high dielectric mean if we're comparing it to some sort of Drude model?
Well, Drude model's for metallic conductors, right?
No,
For metal.
the dielectric second order,
The second order dielectric,
where we have the dicey patterns.
you mean if we have a positive nucleus and an electron cloud around it, and we apply an AC field to it, then the electron cloud sort of is stretched back and forth around the nucleus, creating a displacement current. That's how we model permittivity itself, right? So you're saying, how does a higher permittivity relate to that model?
Yeah, like what is happening physically here when we are wanting a high material?
So remember, the P here is the number of dipole moments per unit volume, right? And epsilon r is related to P through epsilon naught chi E times E, right? So this is probably a very dense material if it has a high permittivity, because it has a lot of polarizable atoms per unit volume, right? The higher capital P is, then the permittivity should be most likely proportional, right? Okay, good. So if the reflection coefficient is about plus 1, that's the same reflection coefficient as a perfect magnetic conductor or a PMC wall, a magnetic wall. That represents a PMC boundary. Thus, we may model the dielectric resonator as a cavity with all PMC walls. So it's a closed cavity with PMC walls. Now it's exactly like the PEC cavity we studied earlier in this chapter, except now it's made with PMC walls, right? And it has some epsilon inside. Yeah? All right, so the process to the solution should be relatively straightforward. The model is approximate, however, and represents a good first order solution to gain insight. So how do we solve this? We've done this 100 times now, and I'm telling you guys over and over again, that we're going to always expand fields and apply boundary conditions. And then we're going to solve for unknown coefficients, right? That's all we've been doing in this whole book. So the boundary condition here is H phi. This is a PMC. So H goes to 0, tangential H. The tangential H to the walls of a cylindrical cavity are phi and Z and rho, I guess, if you're at the top or bottom, right? So here we have on the side walls, the tangential components are phi and Z on the side walls. And on the top wall and bottom wall, it is rho and phi, right? Tangential components. All right, so there are two sets of boundary conditions. We can either use this pair or this pair, but this pair only uses one field component, so it's easier to use those. So we're going to calculate H phi. For the TE to Z modes, we can construct those using an electric vector potential with only a Z component. As we have done before, here is that Z component, and this is the general solution for a cavity, right? We have both standing waves in Z, standing waves, periodic waves in phi, and we have standing waves in rho, right? Good. H phi we can calculate directly from Fz using this expression here, which we get from Maxwell's equations after we apply the definition of the electric vector potential being the negative curl of, or D equal to negative curl of F. And then we apply Maxwell's equations. Okay, so we have to differentiate with respect to phi and Z. So we differentiate these two terms and these two terms. In doing so, we pick up an M from here and a beta Z from here, right? All right, now we have to set this expression equal to 0 in order to apply the boundary condition. And doing that results in Jm beta rho dA has to equal to 0, right? So again, we're looking at the zeros of the Bessel function of order M. So we go back to that table and we use those zeros to calculate beta rho in the dielectric as chi mn over A. All right. The other boundary condition now at Z equals to 0 gives us, okay, so now we calculate H phi. We already did that. But now we're going to apply Z equals to 0 first. So all the Z's we set equal to 0. Here we had a sine, and here we had a cosine of 0. So that means we get 0 and 1. That has to equal to 0. But the only way that can happen is if D3 itself is equal to 0. All right. Now we go back in and apply the Z equal to H boundary condition. We know that D3 is 0, so there's only the sine function now. And sine of beta ZH has to equal to 0 now, so we're looking for the zeros of the sine function. And that's beta Z equal to P pi by H. And H starts from 0 and goes to infinity in integer order.
How do we have H divided by Z?
What?
P pi divided by H. If H is 0, it goes to infinity.
H cannot, no, this should be P. Sorry. Good catch. This is P, right? The index P is the integer index. P pi over H. H is the height of the dielectric resonator. Very good. Okay. Yeah, that's correct. All right, the resonant frequencies are found from the separation relation. Now we have beta rho d squared plus beta z squared equal to beta r squared. Beta r meaning beta resonant frequency, which is omega resonance, square root of epsilon d mu d, because this is the separation relation for inside the dielectric. Then we can say F now is equal to this expression for the resonant frequencies. Yes?
Are separation relations a type of dispersion relation because they're relating the betas with the omegas?
Yeah, they definitely are. That's another name for them, dispersion relation. I like separation relation because you arrive at that expression from the separation constants when you solve the wave equation by separation of variables. There's another name for it called the constraint equation because it constrains the eigenvalues to have a certain relationship, or the dispersion relation because it relates omega to beta, right? Very good. I like separation relation though. All right, so the dominant mode then, we can plug in 0, 1, 0 here, and we get the resonant frequency of the dielectric resonator at the 0, 1, 0 mode. We know that chi mn, the first zero of the Bessel function of order 0, is 2.4049 from our table, and we can calculate the resonant frequency of the dominant mode of the cylindrical dielectric resonator?
Pi over H, just redundant, is it goes to 0, or we set P to 0?
Yeah, P0, right? Because it's MNP.
So we don't need so P pi over H squared.
Yeah, well, so this is in general, right? If you plug in 0, 1 here and 0 here, then you get this expression. Very good. All right, so how can we change the resonant frequencies of our resonator? We can change the radius. If we make the radius smaller, then it becomes a higher resonant frequency. And that makes sense, right? You make something smaller, typically it resonates at a higher frequency. Or we can increase the permittivity, and that makes it resonate at a lower frequency or higher frequency as well, because we're effectively making the wavelength longer inside of the medium, right? Yeah.
Can you explain how we model that with PMC?
Yeah. So consider the dielectric resonator made of a very high permittivity, epsilon R equal to 38, like we had with the waveguide that we just studied, right? If it's 38, then you can calculate what the reflection coefficient will be, right? If you had a plane wave on infinite half space, right? There's a plane wave reflection coefficient of 1/2 of a medium being epsilon R equal to 38, and over here epsilon R equal to 1, right? If you calculate the reflection coefficient for that, coming from this side, right? No. What is the reflection coefficient? ZL minus Z naught. Yeah, so it's coming from that side. Sorry, from inside outward, right? Because there's a field inside the resonator, and it's approaching that boundary because it's inside, and it might leak out, right? But if it's a resonator, you want it to stay inside. So you want it to reflect. If you calculate the reflection coefficient here, it's eta naught minus eta, or ZL minus Z naught. And this equation is exactly this, right? If it's mu naught equals to 1, or sorry, mu naught equals to, mu R equal to mu naught. No, that's even wrong. Mu R is equal to 1, so mu is equal to mu naught, right? Okay, so this expression then reduces to this one here, right? As permittivity becomes larger and larger, these +1 and -1 are kind of meaningless, right? So you just get square root of epsilon R over square root of epsilon R in the limit. So then you get approximately +1. The reflection coefficient for a PMC wall is +1. So these things look like PMC walls if you're inside the dielectric resonator and looking out. It looks like perfect magnetic conductor. It reflects like a perfect magnetic conductor, right? Make sense? Okay, yes.
This kind of resonator, we don't have those hybrid modes.
No. Well, no, they're not necessarily hybrid modes. They're TE and TM modes, right? Because now, the reason why is because now we kind of have conductive walls, right? It's all PMC, but technically it's a dielectric, right?
If we take the error of how much is not 1 and put it on DB, would we, that would be like how much, since it's not a perfect magnetic thing, we would see how much it leaks from being PNC by that.
You mean
TBMM.
you want to calculate like a transmission coefficient?
Yeah.
But this, it's also like a first order approximation because this is for a plane wave. There's definitely not a plane wave in the resonator. And it's for an infinite planar boundary. And this thing has curved walls, right? So
Approximation.
yeah, this whole model is first order approximation, right? But it helps you gain insight. Because you want to understand the modes inside, right? And the frequencies of which they resonate at. All right. So using the PMC model, we end up with this expression for the dominant mode resonant frequency. And we can do the same thing for TM to Z, and we'll get, oh man, this is TM. We'll get a prime here instead of the unprimed, right? So now we're looking at the Bessel, the zeros of the first derivative of the Bessel function of order M, right? And we have a table for that. And then these indices start at different places. The dominant mode for the TM to Z modes is 1, 1, 1. And that dominant mode, because of the ordering of the zeros in that table, right? So the first 0, the m equals to 1, derivative of J1 has a 0 before the derivative of J0, right? Go back to the tables and you'll see that. Here's the resonant frequency for that, right? Okay, good. But in practice, that model is only approximate, so we use these other modes. This is what's normally used in practice, called TE01 delta mode for the dominant. So although the PMC model predicts the dominant mode is the TE010 mode, provided that H over A is less than 2.03, in practice, the most often used mode is, the mode most often used is actually the TE01 delta. What is TE01 delta? Normally, M, N, and P are integers, right? And these integers represent the number of half cycles that the fields undergo in their respective coordinate direction. For example, when delta is equal to 0, then that means a whole half cycle fits within the Z direction, right? So the third mode index is normally an integer, represents the number of half wavelength variations the field undergoes in the Z direction for the third index. But now we're considering what kind of field distribution will we get if delta was not an integer. That means that the electric field doesn't sit completely in here like this, half cycle. It actually leaks out the top, right? So it's like that more, right? Which is a better model for what the fields would look like, right? Okay, so delta is now not an integer. It's less than 1. And the dielectric resonator field of the T01 delta mode undergoes less than one half wavelength variation along its length h. So it kind of evanescent tails out into free space in the vertical direction. All right, so consider this figure on the right where we've put PEC plates between Z equal to minus H2. So there's a PEC plate here at minus H2. And one at Z equal to H, which is the height of the resonator, plus H1, some other height. Why are we doing that? Okay, so it's a way to calculate what the wave number should be in this resonator by sandwiching it in parallel plate waveguide. Then the problem becomes more of a mode problem instead of an infinite free space kind of thing, right? You kind of restrict the eigenvalues that way. All right, to be discrete. So, okay, good. So there are two PEC plates. Anyway, we're not going to use that. We're going to use the results derived from it, but this is how they arrived at these results in your book. And if you use that assumption in that model, then what you find is beta ZH is now not just Q pi over H, or it was P pi over H before, but now it has these two additional terms because it's a delta, not a 0, right? Delta is less than 1. All right, good. So psi 1 over 2 is that. Psi 2 over 2 is that. There's an alpha 1 here and an alpha 2 here. Then there's the H1 and H2, which is the height, the distance between the resonator and the parallel plates, right? All right. And you can make those sort of any value you want. But anyhow, when Q is equal to 0, the mode TE01 delta now, where delta is a non-integer and less than unity, is calculated like this. So you can calculate delta. And it signifies the variation of the fields between the ends of the dielectric resonator at Z equal to 0 and Z equal to H. So you can use that to find, multiply that by beta Z, right? Or here, right? So you have these, you can use these expressions to find what the field distribution of the TE01 delta mode is. Okay? All right. I think Pozar's book has a good read for these dielectric resonators if you want to read up more about that. Okay. That finishes our chapter, lecture 2, right? And now we're going to get into the next chapter. This one's a short chapter. We'll finish this next lecture. And then we're going to get into method of moments and integral equations. So things will start to be exciting. When you guys come to class on that day, we'll have streamers and balloons. All right. So, all right, good. So let's get into lecture 3, spherical transmission lines and cavities. We're only going to study the sphere. Okay, so it's hard to make transmission lines out of spherical waveguides and things, right? What is a spherical waveguide? It's a cone, right? A biconical cone. There are modes in there. It's in your book. We're not going to study that. We are going to study only the spherical cavity, right? Because you need to get used to using the spherical mode functions, and it's easy to study. The book only gives you the biconical waveguide and the spherical cavity. That's it. The chapter is very short. So we're going to go through the cavity. But before we do that, the chapter opens up and introduces how to construct TE to R and TM to R solutions. So whoever was in the class last semester will have seen some of this before, but last semester was taken from this part of the book, right? So this chapter, the beginning of the book, is how to calculate TE to R and TM to R mode solutions, right? So we're going to revisit that first, and then we'll get into the spherical cavity next lecture, and we'll be done with that. And in the following lecture, we're going to study integral equations. All right, so although we have studied auxiliary vector potentials in detail in the previous course, and we've been using them already in the lectures 1 and 2 of this course already, but we're going to revisit them here for the purpose of understanding how TE to R and TM to R modes are constructed in spherical coordinates. You already know how to do this, right? TE to R means what would I want for TE to R modes? What kind of potential would I want? FR, exactly. TE to R, I use an FR, right? So a vector potential with only an R component. TM to R, I use a vector potential with only an R component for A, right? And then you take the curl of those respective things and so forth. But in spherical coordinates, it's a little more involved, so that's why we're going to go over it. So the vector potentials are typically used to solve an homogeneous wave equation when the right-hand side is not equal to 0, right? We did that last semester. Over here, we will use them to derive a homogeneous wave equation for TE to R and TM to R waves in spherical coordinates, right? TE to R are waves with the electric field orthogonal to R, obviously, because it's TE to R, and TM to R are waves with magnetic field orthogonal to R. All right, so remember from last semester, if we have sources J and M, and we want to solve Maxwell's equations, sources are usually the input to Maxwell's equations, right? And we want to find, not the output of Maxwell's equation, the solution to them, E and H. So one way we can do that is to take the direct path by doing integration, right? But we found that direct path is difficult because the right-hand side of the equation you derive relating E to J has derivatives on J, and it's hard to solve an inhomogeneous PDE that has derivatives on the right-hand side because we want to use the concepts of linearity and Green's functions and so forth, and convolutions. So instead, we take this alternate path, integration first, to relate A, an alternate, or not alternate, what am I trying to say? Auxiliary, yeah. An auxiliary path where we calculate an intermediate quantity called A. We relate that to J. This is a direct, the wave equation to derive relating A to J has no derivatives on the right-hand side. So we can easily solve that. Then we can calculate H or E from A or F directly using the differentiation path once we obtained A, right? Okay, so that's the idea. So the vector potential allows for an alternate approach to solve for E and H given J and M. An intermediate quantity A and F is calculated first, which is typically easier to obtain from the source J and M than the fields E and H directly. All right, so let's construct what this mathematical vector field A should be. We will give physical insight into it later, but for now it's just a mathematical construct. The vector field A will relate H. We'll relate to H as H equal to 1 over mu curl of A. So here's the first thing we define. H is equal to 1 over mu curl of A, or B is equal to the curl of A, right? If B is equal to the curl of A, we have to make sure that this definition satisfies all of Maxwell's equations, right? Or else it's no good. So the first thing we do is we go and make sure that Maxwell's equations are satisfied with this definition for the curl part of the vector field A. We set it equal to B. All right, so let's check them one by one, Maxwell's equations, right? The divergence of B is equal to 0 is magnetic Gauss's law. So we have a definition for B now. B is equal to the curl of A. So divergence of the curl of A has to equal to 0, and it does because the divergence of any vector field, the divergence of any curl of a vector field is equal to 0, right? The divergence of the curl is equal to 0.
Is that saying that the curl and divergence are orthogonal operations?
What's that?
That's saying that the divergence and the curl are orthogonal operations.
No, I wouldn't say that. I wouldn't say that. I would say that this vector field is solenoidal by construct, by definition, so it has no divergence, right? It's some rotation about an axis, which necessarily is a closed loop.
But you can uniquely define a vector field by its divergence and curl, right?
Yes, we'll get to that. Very good. We've only defined the curl of A here. So we're free to choose the divergence, and we must define both to make it a unique vector field, right? Very good. So, okay, first Maxwell's equation satisfied. Now we check Faraday's law. Curl of E equal to minus j omega mu H. And we know what H is. It's 1 over mu curl of A. So that equals to minus j omega curl of A. And we have a curl on the left-hand side of the equality and a curl on the right-hand side of the equality. So we can combine them because the curl is distributive. And we get the curl of E plus j omega A equals to 0. Okay. We know also that if a curl of a vector field is equal to 0, then that vector field is?
Gradient field.
Yes, it's a conservative vector field, right? If it has no curl, it's conservative. It means it has a property of independence of path and so forth. And therefore, we can represent that as the gradient of some scalar field. We choose a negative sign because we can, and it will make sense later. So that means E plus j omega A can equal to the negative gradient of phi. Why? Because the curl of any gradient field is equal to 0, necessarily. And we could put a minus here and it's still correct. All right, so this equation now allows us to solve for E. E is equal to negative gradient of phi minus j omega A. If we just had this part here, we've seen that before in statics, right? E equals to negative gradient of phi is what you learn in electrostatics. But now we also have this dynamic term minus j omega A due to the current. The charges are now moving, right? So there's a current. So omega is non-zero. If omega is equal to 0, you go back to statics because there's no time variation anymore. No current, right? All right. Good. So here's an equation for E in terms of its two potentials. Here's an equation for H in terms of its potentials. All right, let's check Ampere's law now. So curl of H, j omega E plus J. This becomes, we know what H is. It's 1 over mu curl of A. And that's still equal to j omega epsilon, but we know what E is now too. E is this, and then we have J here, right? Okay, now what are we going to do here? We have the curl of A. We're going to factor out mu and multiply through by it. So we get the curl of A. We get minus omega squared mu epsilon A from this term and this term, you know. And then minus j omega mu epsilon gradient of phi plus mu j. All right, good. So this equation pops out of the definition for the curl. All right, now we have the divergence of D equal to rho, the last Maxwell equation we have to check and satisfy. So divergence of D is equal to the divergence of epsilon E. D is equal to epsilon E. And then we know what E is. It's minus gradient of phi minus j omega A. And then we can divide through by epsilon, right? And we get this following expression here at the end of everything. There's another wave equation for the potential, right? All right, these are almost wave equations, but they have this extra term here, and then there's an extra term. Yeah. So what can we do? Remember the Helmholtz decomposition theorem from lecture 1 of last semester states that a vector field is uniquely defined only when both its divergence and curl are defined. So we're still free to choose the divergence. We've only defined the curl. So we defined the curl already. We're free to choose its divergence. We choose the divergence in this way. And if we do that, all these expressions that we derived with this thing called the Lorentz gauge allows us to reduce the expressions to these following expressions. And now we do have a wave equation, right? This wave equation here links J to A, right? If we go back, that was one of the things we needed to do. We needed to link A to J. So we derived the wave equation in A that we can solve given a J. Then we need to find H and E given the, or having, given the A, and that's this expression and this expression here, right? But did we get rid of the phi even? And you can express E completely in terms of A, like this, because you can express phi in terms of divergence of A now, right? All right. Okay, so we'll come back to this next lecture, but we're going to derive a wave equation in spherical coordinates. Then we're going to use those solutions in the spherical resonator. All right? All right, any questions? All right, good. So you'll get another homework on Wednesday for the cylindrical waveguide chapter. All right? And then you'll get maybe 10 days or so, or we'll see if you guys need time for that. All right? Good. All right, see ya.
You're really excited for it. I have no idea. I'm gonna be learning all new stuff that I've never seen in my life. Really fun stuff. I like it.
If you like math.
I like math. I like math that doesn't make my head hurt. A lot of this.
It's all about breaking up like an integral equation into a linear equation.
Oh, that's cool. Because I'm not good at calculus. So it makes calculus easier.
Yeah, so what you want?
Well, there's might be some calculus still involved.
Well, I have to accept that.
Yeah, why don't you come to my office?
Can't get away from it. I don't remember any of my like old like techniques for integration and derivation, like separation of variables and stuff like that. So I never like. I feel like once you're out of the math class, you don't really have to do them directly like that.
Yeah. Well, yeah, it's funny because now I'm like, I'm gonna go back and relearn numerical integration techniques.
Okay. I'll buy my office.
Trapezoid. And like, see which
Oh,
one's gonna
God.
be like, you know, the most efficient to do.
Bye.
Wow.
Maybe later this.
I don't know what he wants to do. You guys, see ya.
Thursday, not too
At
late.
least at the start.
Yeah, Thursday would be good because then I have all these
Yeah.
things that I'm.
I mean, we must end up doing method of
On the
moments.
Thursday,
It's
like-
like I keep seeing it pop up everywhere.
In the
for
morning,
fun stuff.
Yeah, Thursday's fine.
Totally numerical, so.
All right, see ya.
There's other gauges that exist too, right?
There are.
Lorentz gauge.
Yes. Coulomb gauge, you just set A equal to 0.
Yes.
There.
Okay, yes. Yeah, I've seen that one too. Because I was getting confused because I feel like in one class, we were just using E equals J omega A.
You can do that in the far field.
Hmm.
Because remember that E minus gradient phi, E equal to minus gradient phi is a statics thing, right? Statics contribution, and that has one over R squared and one over R cubed dependence. So if you go to the far field, that part goes away.
Gotcha, okay.
There's a more formal derivation mathematically of how, you know, part of the minus j omega A radial part cancels the that minus gradient phi. But maybe that's what's happening.
I saw that whole thing in the class, it was like, it's A minus radial.
Yeah, exactly. Minus j omega A, you only keep the trends state and phi. Radial part dies out. All right, very nice. See you guys.
Where to make my antenna stuff in my exactly what you're talking about.
No, I think the
Oh, yeah, well, after we did it, we just, now we're getting But I'm also not really clear. Should ask. One is asking us for this really. How do we know? Well, the separation one. The separation. Yeah. If looking for you take the wave equation. Yeah, that was. I hate the way that, like, people just go back to what they can. I've seen people in one derivation, like use beta and then do excellent, but it's documenting because they'll do beta and then they'll write K and then later same with so like. Yeah. Yeah, you be careful.
Like,
Good. You play the basketball?
yeah. I forgot to bring my computer today.
You didn't bring your computer?
So it was very nice.
I need to read the chapters in one about this. I don't know. I don't know anything. All I know is that it's like a sine wave, but it falling. I mean, I don't know. I thought I was way worse off than I am. So I'm glad. Yeah. I'm not sure honestly. He must be having a meeting. I know he's a meeting right now. But he doesn't do this line. He didn't mention.
So do you have the midterm and the final exam for the last class?
Which,
Do you have the midterm and final exam for the last class?
which last class?
Like the class
Before?
before that, yeah.
Yeah,
The midterm and final exam.
Yeah.
Take in person?
yeah, in person. I think it's 2 midterms and 1 final exam.
There's some.